Now we discuss the next method, that is called as 2SLS, or it is the full term can be said as two stages least square estimator. This method was given by Thale and Bassman, and again here if you take the structure, the same structural model is stated over here, and the problem is the correlation between YT and UT. But this two-stage least square method, we will now be referring to 2SLS. It says that the total variation in YT can be divided into two parts, systematic and the random part. And only the random part is likely to be correlated with Y. So this is, we call this as a two-stage least square. That is, in the first stage the random part YT is removed, and in the second stage we will apply OLS. So here basically the whole YT is not correlated with U. So we should clean YT or remove the random part from it. Like a systematic variable cannot be correlated with a random term. So what we do, we can do this by regressing income, and here we have income YT, we regressing income on exogenous variable IT. Here we have the exogenous variable IT. So in the first stage, random part from the YT will be removed, and in the second stage the OLS will be applied. So we discussed the first stage. What we are doing, we are regressing income on the exogenous variable IT using the reduced form. So we can write the reduced form. We have seen how to derive the reduced form in our previous lectures. So we simply write it as YT is equal to pi1 plus pi2 IT plus ET. So upon estimation we get the values of pi1 hat and pi2 hat. So YT hat is equal to pi1 hat plus pi2 hat multiplied with IT. And we can say that now YT is equal to, what we are trying to find, YT is equal to YT hat plus ET, where this YT hat is the systematic part and ET is the non-systematic or the random part. Now this YT we are writing again in the second stage, we are taking it in the inside, we are breaking the function of YT, breaking the term YT in the CT function as YT hat plus ET, and that has been done by just now we have taken the reduced form and then we have got it from there, estimated it from there. So CT is equal to beta alpha plus beta YT plus UT. Now this YT we are dividing into two, so CT is equal to alpha plus beta YT hat plus ET plus UT. So now we can open the brackets and say CT is equal to alpha plus beta YT hat plus beta ET plus UT. Now beta ET plus UT, that is the error, this becomes the composite error term. And now we can say that the YT hat is not correlated with this composite error term beta ET plus UT. So now we can apply the OLS. We get the estimate the beta hat by the formula summation CT YT hat divided by summation YT hat. Now see, we do a small manipulations, like YT hat is equal to pi1 hat plus pi2 hat IT. Now we take Y bar hat, means we take Y bar hat is equal to pi1 hat plus pi2 hat multiplied by I bar. So now we write YT hat minus YT bar hat is equal to pi1 hat plus pi2 hat IT minus pi1 hat plus pi2 hat I bar. So the terms which are highlighted in green, that is these two terms, they can be cancelled out. So what we are left up with is YT hat minus YT bar hat is equal to pi2 hat multiplied by bracket open IT minus I bar. Now IT minus I bar we can write is as small it. So YT hat is equal to pi2 hat small it. Now from this equation we derive two things. We first take the square, so we get the term, and we do the summation. Summation YT hat square is equal to pi2 hat square summation it square, and this yt hat we can just multiply with ct also. So ct yt hat is equal to pi 2 hat ct ci yit. Now we take the summation. So upon taking summation of this term, we get summation ct yt hat is equal to pi 2 hat summation ct it. Now what is the formula for b hat? We have seen in the previous slide, b hat is equal to summation ct yt hat divided by summation yt square. Using these, now we have the term for ct yt hat also, and we have the term for yt hat square also. So both these terms we are having. So we write it as pi 2 summation ct it divided by pi 2 square, pi 2 hat square summation it square. Now the numerator pi 2 hat gets cancelled and the denominator 1 is left. So we can write it as summation ciit divided by pi 2 hat summation it square. Now this pi 2 can also be obtained from our reduced form equation. Yt is equal to pi 1 hat plus pi 2 hat I plus ei. Now from this we get the value of pi 2 hat as equal to summation small I y divided by summation I square, as it is written here, summation yt it divided by summation it square. Now substitute this value in beta. So what was my beta which I have just now derived? Beta is equal to summation ci it divided by pi 2 hat multiplied by summation it square. Now we substitute the value of pi 2. We have just now from the reduced form, we can take the value of pi 2 and substitute it here in the formula for beta hat. So beta hat is equal to summation ci it divided by summation it square. And since pi 2 is in the denominator, we inverse the formula for pi 2 hat. We write it multiplied by summation it square divided by summation yt it. Now summation it square is in the denominator also and in the numerator also. Those two cancelled out, so we can say it is equal to summation ct it divided by summation it yt. This is nothing but equal to the moments of ci divided by moments of yi, that is equal to beta hat. This value, what we have just now is, we have proved that this value is just equal to the value which we have got of beta from the indirect least squares method. So we want to make a statement that if a model, in a model, if the equation is just identified, then indirect least squares method and two-stage least square method will give identical results. Now we move on to the next, that is the recursive models. These are, recursive models are a special type of simultaneous equation models. The good thing is they can be estimated by OLS. Here the problem of simultaneity bias is not present, but the structure, it has a particular structure. See, yit is equal to lambda 11 x1t plus lambda 12 x2t plus ut. In the first equation, both of these terms are exogenous. But when we come to the second equation, these two terms come as it is, but now yit is also present as an explanatory variable. So the endogenous variable is also present in the second equation. In the first equation it was not there. Similarly when we move to y3t, we see that we have this second, we have y1t and y2t which were endogenous in the from the previous equations. They are incorporated as an explanatory variable along with our old x1t and x2t which are continuing since our first equation. So if this particular type of scheme of things is there, then we call it recursive models, and here we can use OLS directly. There are certain assumptions, that is the error terms, they are not error terms of u1t and u2t. they are equal to 0. That is, the disturbance term of one equation is independent of the disturbance term of the other equation. Here y1t, y2t, y3t, y4t, they are endogenous variables, and we have x1t and x2t as y1t, there is a and this x1t and x2t, it is written here endogenous. This is a mistake. It should be exogenous. There is a correction. So x1t and x2t are the exogenous variables. In the first equation, the endogenous variable is a function of exogenous variables only. In the second equation, the endogenous variable is a function of exogenous and the first endogenous variable. In the third equation, the endogenous variable is a function of exogenous variables and the first two endogenous variables. So basically we are seeing a particular pattern of causation and it is moving in a particular direction. In simultaneous equation models, we have two-way relationship, like consumption is determined by income and income is determined by consumption. And this, because of this, there was a problem of simultaneity and there is the problem of bias. But in recursive models, we find cause and effect relationship are only in one direction. Meaning thereby, if you see the equations that have been written over here, y1 is determining the value of y2, but y2 does not influence the value of y1. Again, next time y1 and y2 both determine the value of y3, but y3 does not determine the value of y1 and y2. So that is why the problem of simultaneity is not there. Simultaneity bias is not there. Means y1 is determining the value of y2, good, but if y2 also is determining the value of y1, then there is a problem. But in this system of models, y2 is not influencing or not determining the value of y1. So there is no problem of simultaneity bias over here, and we can use OLS. So there is a particular pattern of causation in a particular direction, and the cause and effect relationship is only in one direction. Now, the features, they are also called as triangular models. Now here beta is a matrix of coefficient of endogenous variable. It will always be a triangular matrix, that is this recursive matrix. In the triangular matrix, what you mean, the upper elements of the elements above the diagonal, they are all 0. As in the matrix you can see, and we have only the non-zero elements in the lower half of the matrix, that is beneath the diagonal elements. The diagonal elements are all here -1, -1, -1, -1, and beneath we have beta 2, 1 and beta 3, 1. We don't have anything over here above the diagonal. So as we have seen that the y2 is not influencing y1. Now the covariance and variance of the matrix, this has been derived by the matrix form by using the knowledge of matrix. I hope you have the basic knowledge of how matrix multiplication is done. So your matrix U is equal to U1t, U2t, U3t and U4t. This is a single column matrix, and if you take the transpose of it, you have U1t, U2t, U3t and U4t. It's in as a row. This is the row matrix. Now expected value of U and the transpose of U, you can do it. So now when this is what we have done, means in the multiplication this is multiplied with this, and then we can so it becomes this term U, when U1t of the original matrix is multiplied with the transpose of it. So U1t and U1t, we get U1t square. Next time it is U1t of the first matrix is multiplied with the second term U2t. So we get the expected value of U1t, U2t. Next time U3t of and this is again with the same matrix, not with UT. This is a correct, I said something, I just prompted something wrong. So U1t, first we multiply with U1t, then U2t, again we multiply with U2t of the transpose, then U1t we multiplied with U3t, so it becomes expected value of U1t, U3t, then again U1t we multiplied with U4t, so we get U1t, U4t. Likewise, this is one extra column is written. Please ignore the last column. of the square matrix, please ignore this last column. So again this column would have come if there was again u5t. Next time we do the multiplication of from the normal from the original matrix of u2t multiplied with u1t of the transpose. Then we get u2t uit. Then again u2t multiplied with u2t, so ut2 is u2t square we get. Then again u2t we multiplied with u3t. So we get the term expected value of u2t 3t. Then last time we get u4t multiplied with u4t. So we get expected value of u2t multiplied by u4t. Same thing we do. We take again u3t, we multiply with u1t, u2t, u3t, u4t of matrix, and in the last term we have u40. u40 we multiply with again u1t of the transpose, again u2t of the transpose, u3t of the transpose, and u4t of the transpose. So this multiplication we are doing, and also please ignore the last ignore this column, the last column and the last row. This is an addition. If we have this u5t variable, then we will be getting this. Since we are having only taken 4, we will not be having this. Now, so what we find, see, u1t, u2t, expected value of 2 error terms consecutive, 0. u1t, u3t, expected value of 1 error with the other error of the other time period. By assumption, it is 0. So all the terms which have different use of different time periods, they are 0. All terms are 0. This is 0, this is 0, this is 0, this is 0, this is 0. What we are left with, the diagonal elements. If you see the diagonal elements, they are u1t square, u2t square, u3t square. So these diagonal elements are sigma square and the off diagonal elements are 0. So what we can say, we get a diagonal matrix. Now, so the recursive models, if your system of model is satisfying, we can, as I am repeatedly saying, we can estimate it by OLS. Now, we go to the last method, 3-stage least squares method, or we call it 3SLS. See, we have seen that for various reasons we include explicitly in a relationship only the most important 3, 4, 4, 5 explanatory variables. In that case, we leave the others, or we say what are not very important, we leave them out of the estimation process. And we go by this implies that, or we assume that these things will be sitting in the error term. The variables which we have not included in the model or we have excluded from the model, their effect is there in the error term. So if some variables are omitted and from the relationship, it is possible that the use of this relationship are correlated. That is, the error term will be correlated, and hence we have to apply the 3-stage least square method. It was given by Zellner and Thiel. It is basically an extension of the 2-stage least squares method of Thiel. It involving the application of the method of least square in 3 stages. So as we apply the same process of, we do the same process of 2SLS, that is 2-step least square method in the first 2 stage, and the only difference is here we use the reduced form, and in the final stage we apply a completely new method, that is generalized least squares, GLS method. So this is a very tedious process. We just have an introduction of how this process is done, but discussing GLS will not be feasible in a lecture over here. So let us go quickly through the assumptions of 3-stage least squares. The whole specification, all the specification is known. There is no serial correlation. The random variables of the various relationship of the system are contemporaneously dependent. The model is over-identified, and we do not consider the identity equations. We use them only in the process of elimination. So these are some of the assumptions, that there is no serial correlation, the whole specification is known, and the random variables are contemporaneously dependent on each other. Otherwise, we will not be using this. method, and the model is over identified. See, we have a G system, there are G endogenous and K predetermined variables. So G system means we have Z1, Z2, Z3, Z4 and it will extend up till Zg. Now here Z1, Z3, they are all endogenous. So in the first equation, Z1 is equal to A12 Z2 plus A13 Z3 plus A1G Zg. So these which are highlighted by green are the endogenous, and what are highlighted by yellow, they are the predetermined. So the first equation then again has the term alpha 11 B1 plus alpha 1k Bk. So these B1, B2, B3, B4, B5 extending up till Bk are the predetermined variables. Similarly, we can have Z2 equation. This is equal to A12 Z1 plus A23 Z3 extending up till A2G, because we can extend up till G, Zg plus alpha 11 B1 plus alpha alpha 21 B1 plus alpha 22 B2, like they will extend up till alpha 2k Bk. So we have the system of equations showing the relation. We have this in the equations, we have both the endogenous and the predetermined variables. Now what we do next, we multiply each equation by the predetermined variables. We multiply each equation by the predetermined variables. So meaning thereby in the first equation was Z1 is equal to A12 Z2 plus A13 Z3 plus A1G Zg plus alpha 11 B1 plus alpha 1k extending up to Bk. Now this we multiply by B1. B1 is your first predetermined variable. So B1 Z1 can be written as A12 multiplied by B1 Z2 plus A13 multiplied by B1 Z3 extending up till A1G B1 Zg plus alpha 11. B1 is already there, so B1 square plus it will extend up till B1k alpha 1k B1 Bk plus B1 U1. Now the same first equation Z1 will be next time multiplied by the second predetermined variable, that is B2. So the same thing we get, B2 Z1 is equal to A12 B2 Z2 plus A13 B2 Z3 extending up till A1G B2 Zg plus alpha 11 B1 B2 plus extending up till alpha 1k B2 Bk plus B2 U1. So if we are multiplying the predetermined variables which are there in the system of equation with individual equations. So in this we can see that the original equation is not highlighted in the first two equations, they are of the simple. Now in the first equation we are multiplying by B1, and see B1 is multiplied to all the terms in the first original equation. In the second one, B2 is multiplied to all the terms in the second equation. So we are multiplying all the equations by k predetermined variables. So now we have k forms for all the G equations. This is what we have done in the previous slide, and it is shown together. So B1 and B2, they are the predetermined variables. Now we multiply the second equation. Now we have done it for the first equation Z1. Now we do the same process for the second equation Z2. So we have the, if you recall the Z2 equation, Z2 is equal to A21 Z1 plus A23 Z3 plus A2 Zg plus alpha 21 B1 plus alpha up to extending up to alpha 2 Bk. So this we multiplied by B1, so it becomes B1 Z2 is equal, now we are doing multiplied by Z2. So that is why Z2 is highlighted over there. So B1 Z2 is equal to alpha 21 B1 Z1 plus alpha 23 B2 Z3 extending up to alpha 2G B1 Zg plus alpha 21 B1 is already there, so it becomes B1 square plus alpha 2 is extending up to alpha 2k B1 Bk plus B1 U2. So this is what we have done. Now in the second time we will multiply the same Z2 original equation by the second predetermined by B2. So this one will go on continuing. We are for z2 we will do the multiplication with the with the second predetermined variable, and the same process can be repeated. So finally we give the overall structure by multiplying. Now for the gth equation we multiply by b1 and b2, and so finally we get a structure that is given over here. We are simply multiplying the ordinal equations by predetermined variables one by one by one. So the first equation becomes, let's take the last equation, bkzg. K is the number of predetermined and g is the number of the variable endogenous variables and the number of equations. bkzg is equal to ag1 bkz1 plus ag2 bkz2 plus extending up to ag1 b1 bk plus and extending up to a gk bk square plus bk uj. So this is our system of equations. Now to estimate what we do, we first do the reduced form of the equations. First we do the reduced form of the equation. So z1 we now write it only in terms of b1 and b2 and bk, which are the predetermined variables. Similarly, z2 we write it only in terms of predetermined variable. z2 is a function of b1, b2 extending up till bk. So we have done the reduced form. What is the beauty of the reduced form? The endogenous variables are explained only in terms of predetermined or exogenous variables. From this we estimate the values of z1 hat, z2 hat and z3 hat. From this we get the equations of z1 hat, z2 hat and z3 zg hat. Now we have in the earlier portion of the slide we have written the structural equations. Now what we do, we have just now estimated the value of z1 hat and z2 hat. We put those values over here and then we put the values of the estimated z's in these structural equations, and then we apply the method of least squares. So using this, what we are doing now, we get the values of, from here we know the values of this, we have estimated the values of this from the reduced form earlier. Now we can estimate the value of a12, a13, a1g and alpha 1k and alpha 2k, and for the second equation we know the values of a2. From here we can estimate a21, a23, a2g and a21, alpha 21, alpha 2k and likewise. So now we can estimate the value of alphas and betas. So this process is nothing but the two-step least squares method. So in the process we get the error terms E1, E2 extending up till Ej for the structural equation. Next we calculate the variance, that is sigma square E1, sigma square E1, E2 and likewise now we can calculate the covariance, that is sigma hat E1, E2, that is equal to summation E1i multiplied by E2i divided by n, and also we can do the covariance of sigma hat E1, E2, E3 is equal to summation E1i summation E1i multiplied by E3i divided by n. We can go on doing the calculation likewise. So we get the error terms, we can calculate the variance, we can calculate the covariance, which are needed for the GLS method. So using this variance and covariance we perform the transformation of the original variables and then we apply the method of GLS. In this class today we will not be able to explain the concept of GLS, but these variance and covariances are required for their estimation. But as a concluding note, the 3SLS method is more efficient obviously than the 2SLS method, but it's a very tedious process and it requires the complete knowledge of the model specification and all those things. And if the random variable are contemporaneously independent, we've used this when these random terms are contemporaneously dependent, but if they are contemporaneously independent, then there is no difference between the 3SLS and the 2SLS models. So means what we want to emphasize is, we use this in special cases only, or else 2SLS method is also applicable in most of the cases. And here we need the application of reduced form and 2SLS, and then we move on to the method of generalized least squares estimation. So I hope today's lecture on estimating simultaneous equations is clear to you. Thank you.